Welcome everybody on Zoom, welcome everybody in the lecture hall. Today we are going to continue our exploration of the SQL language, looking at the queries that we can write. I'm also going to take some time, there are a few questions in the element chats that I would like to discuss also directly. And I will have a question on Clicker also for you, and then we will continue. So maybe we can start right away with the pending questions in the element chat. So the first one, go ahead, Mark.
Okay, so the first question was, it says duplicate elimination is superfluous for selection queries. So I am a little confused whether duplicate rows actually do get still displayed if they match the criteria, or do they not?
So here, what I meant with the notion of eliminating duplicates was purely, I would say, an implementation thing. Technically, in the set theory, in the set version of the relational algebra, meaning that you have sets of records, you anyway never ever have duplicates, right? Never. That's by definition of the theory. But what I meant is when you actually do it on paper, and you follow the thing, like, for example, you use selection and then you cross away, you cross out all of the records that do not match the duplicates, and then output what you get. What I'm saying is that when you try to do it on paper, you don't need to worry about whether there can be any duplicates, because by design, if all you do is cross out records in what was already a set of records, that will not introduce any duplicates, right? So this is why I said you don't need to worry about duplicate elimination, right? So that was the first one, I think.
There was a second question about the difference between extended projection and renaming attribute. And the question was, is the difference that the extended projection just renames the attribute temporarily for displaying, whereas the renaming will change the name of the attribute in the particular table for good?
So here there are several things. First, you could consider that renaming is a special case of the extended projection if all you do, if you don't compute anything, you don't add anything, you don't multiply anything, and you just take a column and give it another name. So you could consider that you could actually forget about renaming and just use the extended projection to also rename columns. But in practice, when you just rename a column, people prefer to use the row operator for that. The second thing in there is there is no, in the math, there is no notion of distinguishing between on the fly or not on the fly, right? It's like when you manipulate numbers in math, right? You start with 4 and you do 4 plus 2 and you get 6, right? But 4 is there, 6 is there, 2 is there. These are just mathematical objects, right? All you're saying is if you take 4 and you add it with 2, then you get 6. So what happens with the tables, with sigma and rho and pi and all of these things, these are just mathematical equations. So all we are saying is if you take a table and you take sigma or rho or whatever of that table, then you get that other table. This is a mathematical equality, right? But in math, you don't modify anything. You just take a table, you use some operator, and that gets you another table, right? The notion of changing or updating, that's a computer thing. That's something you do with a computer program when you have something in memory that you change, right? But in mathematics, you just have objects, mathematical objects that are in relationship with each other, like relational tables. Okay?
The last question is, will a join only work if both the name and domain of the colliding attributes are the same? And if not, when colliding attributes are different names, then the only way to join is by using the theta join.
Yes, that's exactly the idea. So the natural join is when you have the same column name on both sides, and when it is also your intent to actually join using that attribute, then you go for the natural join. But if there are no columns in common, and you still want to join on this and that, and you know exactly which columns you want to join together, then you use the theta join. This is what it's for, and then you can be explicit on the actual formula that you use. It could also be the case that the two tables that you want to join, they do have column names in common, but it might be that it was a coincidence that the column name was in common and you don't actually want to join on that. Then also in that case, you should use a theta join instead. Right. Okay.
Just one remark, he was also asking if both the name and domain have to be colliding.
So if you look at the theory, the way we defined it in the theory, if the domains are disjoint, the natural joins test for equality, right? So if you have integers and string, mathematically an integer will never be equal to a string, right? So in that case, the join predicate would always fail and you would have nothing. Now the other question is, what about SQL products? What about the real life SQL products? And here I think we should experiment and see what PostgreSQL does. Like try to define a table with a column foo that is an integer and a column foo that is a string. Several things could happen. Either it would work and you would get something empty, or maybe it will you get an error, or maybe it will attempt to force the integers to be transformed to strings. So these are the things that I think would happen. And this is something we will experiment. You can actually also experiment if you want, and we'll tell you what happens. But whatever happens will be specific to PostgreSQL, and I cannot guarantee that MySQL or Oracle or IBM might not behave differently, right? Okay. So we don't have any pending questions anymore, right? Everything else was answered. All right, so now it's my turn to ask you a question on the Clicker app. This one. So I'm giving you an input table that is somewhere in a PostgreSQL database. It's called my table, and it has these columns A, B, C, and D, and it has a few values in there. I didn't specify the domains, but you can kind of infer them. Don't worry about the red underline. It's just when I took the screenshot, I didn't see that it was doing that, but this has no meaning. And the output I would like is this other table with A, E, and D as my columns, and with just one bracket with the values bar2 and bar. So I'm giving you 4 queries, and I'm asking which one of these 4 queries is giving me that. So for these kind of questions, you have several ways to proceed, right? You could take each answer and try to calculate the output of the answer. This would be one way, and then you get 4 outputs and you just pick the one that matches the desired output. Or you can also proceed by elimination. You can directly see that in a query, there are clues that tell you that anyway, there is no way this can output what is on the top of the screen, right? So then you can eliminate a few of the queries just like that. And that restricts the computations you have to make. All right. Okay, there is a majority, and the majority is correct. Congratulations. So here, what you could see very quickly is that since you want the columns A, E, and D, you can already eliminate the first and the third one because they do not rename the columns, right? You have A, B, and D in that case. So it cannot be the first and the third answer. So it's either the second one or the last one. So if you look closer, B is smaller than C strictly, and A equals D. That would be here and here, right? It would be the second and the third. 1 and null, if you say B smaller than C, would be this 3-valued logic. is 1 smaller than null? The answer is unknown. We don't know what that null is. Could be 0, could be 2. We have no idea. So this B smaller than C would give you unknown, right? It's indefinite. And A equals D. Only select this one, the second one. You see bar here and bar there. Foo bar and bar foo, it's not the same value. So this is excluded. So you get this one. And then if you only keep A, B, and D, so you remove the third column and you rename B to E, you see it's bar to bar. You get exactly this, and B is renamed as E, right? So you get the second answer. And the last one, B is greater than C. You see that it wouldn't select anything in there, right? And on top of that, it would ask, on top of that, that A equals D is not unknown. That's equivalent to saying that neither A nor D is null, right? But since there's never any null here and any null there, this would always be true here, right? But since we ask that B is greater than C, this just doesn't happen, and that doesn't give us the results. For whom is that clear? All right, perfect. Yes, we have a hand microphone instead of the catch box.
You could please scroll down. Just let's say we run I think is okay.
The first one, the third one.
That makes the calculation B greater than C, and it's actually unknown.
Yeah.
Will the query, what will the query return? Like an error?
No, it will just not include it. It will, in my understanding, it will keep all the true. It must be true. If it's unknown, it's not going to keep it. Yeah. So it's 3 values. Sorry?
You need to be careful.
You need to be careful, exactly. The core part to understand is SQL has a 3-valued logic. It's not just true and false, it's true, false, and unknown, right? So you need to always keep that in mind. And whenever you have nulls, then this is where the unknown can actually start appearing. Okay. All right. So now let me switch back to the slides. Okay. So let's take it from where we were last time. So we had a query with select as from where order by limits and offsets. These are all the clauses we've seen so far. I have summarized everything on a single slide where you can see all of that. I have good news for you. SQL is very constrained. You cannot do whatever you want. And in particular, this means that these clauses that you see here, they always appear in that order. You cannot do it in a different order. For example, if you try to do, I don't know, select where limit order by from, you will get an error. That doesn't work. It has to be select, then from, then where, then order by, then limit, and then offset. Okay, very important. So you can learn it by heart in that order, select from where, order by, limit, offset. Some are optional, of course. You don't have to have them all. You can skip the where, or you can skip the limit, or you can skip the offset, or you can skip order by, limit, offset, and so on. The only thing that I told you to be careful about is do not skip order by but still having limit and offset. This I told you doesn't make any sense, right? Limit and offset only makes sense if you have the order by. I'm saying that because you wouldn't get an error. You would just get something unpredictable. Okay, so this is where we were. Right? And you have the as for renaming. So we have, you see everything we have here. We have projection in here, right? We can project, we can rename here. We can select with the where clause. Be careful, not with the select clause. Selection is the where clause right here. We order by the birth date and we limit and offset. Okay. Okay, let me add more clauses because more clauses are going to come. So we'll have an even bigger list of clauses that we can have. This is actually super, super important because aggregating is one of the very core use cases of data analytics, right? It's the first thing you want to do when you have a huge data set. You want to aggregate things and get some high-level statistics. That's what I said last time, that the Federal Office of Statistics in Switzerland is probably spending 90% of their time doing that kind of queries. Okay, so a bit of a reminder of what we saw in the theory of the relational algebra. We have all these Greek letters, and in that case, the Greek letter that we used for aggregations was gamma, right? This is a gamma. And you might remember that in the gamma, we had a comma-separated list of things, right? So you look for the commas to separate them. Some of them are just attribute names. We called them the grouping keys, country and city. So we group a country and city. And everything else that is not just a column name is basically an aggregation on a column, plus you give it a new name, right? So here we sum over the prices and call it volume, and we count the customer and call it non-transactions. Is there a question on the Zoom chat?
Yeah, there was one comment on the Zoom chat. The last slide output should be James, I think.
It's entirely possible. Let me do it with you. I need to open the chat and close the chats to make it happen in the room. Yes. Okay, so select first name and last name. So that would be, okay, the first and the third column, where original series is true, so that eliminates the one in the middle. So we have James and Spock. Then we order by birth date, so that's ascending by default. So the smaller one is 2230, and the second one is 2233. And since we offset, we skip the first one, which is indeed Spock, and we take the second one with a limit of one only. That's, yes, you are correct. The answer is James Kirk, and I will fix it. Very good catch. I didn't do it on purpose, I promise. I never intentionally do mistakes, but in that case, you caught one. Thank you very much for that. That's great. Right, so I'll fix that in the final slides. Okay, so let's go back to our aggregation. So we group by country and city. So this is the colors. I put it with the colors. So we get here one record for every group, every unique global value here, Switzerland, Zurich, Germany, Berlin, Germany, Frankfurt. We have these new columns that are on the right side of the arrow, right? So volume and non-transaction. Volume is a sum over the prices. So this plus this gives you this plus this gives you this, and this gives you this. And here we count the customers. So there's two of them here, two of them there, and one of them there. What's important is that count by default is throwing away the nulls if you do it on a column, right? Here we don't have any nulls, but I will come back on that. Okay, now, this is how you do it in SQL. That's a new clause that is not very surprisingly called group by. And in group by, you specify your grouping keys, right? So the grouping keys, remember that in the gamma notation, these are all the attributes that are on their own, right? So in that case, it would be group by country, city, right? But in that case, we group by century. Where is it? Where is it? Here. We group by century. So we have one group with these two and one group with these two records, and we output one record for each one of these. And count star doesn't even specify any attributes. It's actually kind of a cool thing that makes it easier for the people to use. It just counts the records, right? This is what the star means. So we count the number of records, and here we don't care about nulls. We just take all the records that we find. So how many records do have the 23rd century? Two of them, this one and this one. How many do have the 24th? This one and this one, two of them as well. This is why you get two here and two there. You will notice that when you group by here, the domain is preserved, right? So the century was an integer, so you preserve the domain here. And when you have a count, PostgreSQL kind of automatically assigns types. So when you do count, it's going to use big int, and big int, you might remember, is a 64-bit integer, which means that you can go all the way to 16 quintillion records. And I can tell you, if you manage to store 16 quintillion records on your laptop, then I want to see your laptop, because that's more than you need. Okay. All right. Now you can also rename. So here I didn't rename anything, so it just called it count, right? But I can give it a name explicitly and call it count, right? In that case, that would be the right side of my arrow in the gamma notation, right? Okay. I put in green here century because that's a special column. It's a grouping column. You might also hear grouping key, right? You group by that. So the grouping column is in the output, the first one, and the others are the non-grouping columns, right? So whenever you group on a table, that automatically splits the columns into two kinds of columns. There's the grouping columns and there's the non-grouping columns, right? So you put them into two categories. Okay. And what you can do next is that you have to aggregate over the non-grouping columns, right? What you cannot do, this is a counterexample. Why can you not do that? Because here you're trying to output the column H, but you're not grouping by age, you're only grouping by country. This doesn't work because if you tried, as you know, to make a wild guess about the sort of things that this could do, this is just not a table, right? If you try to say, okay, select all the centuries, then you have 23, it's the two of them, and then you select the age, these two, that doesn't work. We want a single value as the output, right? This is not even a table. There is a vertical bar here, horizontal bar here, but not here. So it's not, it doesn't make any sense. So the rule here is the grouping keys that you have here, you can repeat it as is in your projection, but do not ever, 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 ever put a non-grouping column on its own without aggregation, never. You need an aggregation for the non-grouping column. So in that case, we count, and then we get 2 and 2. So the difference between count star and count H is that if you count on a specific column, it will not count the nulls. If there is a null somewhere, then it will exclude it, right? So for example, if you count on the middle initial, here you see that Spock and Catherine, I removed the middle name, so null and null. If you count in every group, you will only get 1 and 1 because the group of 23 is these two records. But if you count T and null, count only will count T. It will not count the null. This is why you get 1. And if you count on 24, it's these two. So you count C and null, but null again is excluded. So you just get C. This is why if you do count on middle initial, you get 1 and 1. And if you do count on age, you get 2 and 2 because there's no nulls in there, right? And if you do count star, then it doesn't care about the nulls. It just counts all the records. For whom is that clear? For whom is that not clear? Okay, just making sure you're following. Otherwise, you can ask any questions you want, right? Okay, so count on a column when there are no nulls, count on a column when there are nulls, in which case they are excluded, and count star, which is just counting the records without looking at any column in particular. Okay. Next, let me tell you about the aggregation operators. I showed you counts. There are many others that you can use in SQL. There are 5 of them that I think you should know by heart. You should know the list of 5 by heart because this is really the top 5 aggregations that come to mind to any database person, right? If you implement a database, you need to at least support these 5. So it's the max and the mean, it's the sum, it's the average, and it's the count. These are the top 5. You have a few others that are a bit advanced. So this is a bit less important, but it's useful to know that they are here. You can aggregate Booleans. Imagine that you have a Boolean column. You could do an aggregation on end, meaning that it's going to do end. So basically it's going to be true if everything is true and false as soon as one of them is false. Then you have the Boolean or, right? This value or this value or this value or this value. In that case, it will output true if there is at least one true somewhere, and otherwise it will output false. That's the reason, by the way, why the first one is also called every as a synonym. So bool end amounts to saying that everything needs to be true, right? String ag works on string domains. When you have varchar, text, and so on, it's just aggregating the strings. It's concatenating the strings, right? So string ag is yet another aggregation. Okay, so if we come back now to the data, we can use these other aggregation functions like this. Typically, we put them uppercase. This is what people are used to. So here we look for every century, the minimum age, right? So the 23rd, the ages are 57 and 189. Yes, it's in the future, so people live longer, especially from other planets. So the mean here is 57. And for the other 24, we have 35 and 41. So the minimum is 35. Okay, who agrees? Okay, then the max. So in that case, it would be 189 for the 23rd century, and it would be 41 for the 24th century. The sum of the ages, so 23 would be 57 plus 189 gives you 246. And for 24th, it would be 35 plus 41 gives you 76. And then the average age, so 57 average with 189 gives you 123. And 35 average with 41 gives you 38. Okay, now here's an example with bool end. So I'm using a Boolean column. So there is a column here. I think I modified it. Yes, it's a Boolean column that says if it's a captain or not a captain, so true or false. So bool end is going to be false in both cases because you need everything to be true, right? So in the 23rd, you have a true and a false. So true and false is false. And then for the 24th, you have false and true, which is also false. The same with or. In that case, it's true because false or true for 23 is true, and false or true for 24 also is true. And finally, string ag, which is an aggregation of strings. So in that case, for every century, I'm building a string list of the first name, comma separated, right? So I'm aggregating the first name, putting commas in the middle. So for the 23rd century, we have James and Spock, right? So James, comma Spock is going to be this aggregating string. And for the 24th, we have Beverly and Catherine. So Beverly, comma, Catherine. Okay. Who is following? Okay. Who is totally comfortable with what we are doing and finds it easy? Some of you. Okay. Okay, just want to make sure that you're not lost. This normally should be easy, right? These kind of things. And this is also the sort of things you can really play with on the Jupyter notebook. On a database, you can actually write all the queries you want in order to work with that. Okay, now, as always, it's easy to make things wrong with PostgreSQL because it gives you actually a lot of freedom. And I'm going to give you a few rules for the group by that you should really, really pay attention to whenever you use a group by. The first rule that you need to be careful about is that every single column that is a grouping key must be in the output projection. Right. So this is an example here with several grouping keys. So it's like in the theoretical example with country and university. Here we have century and captain. It means that these two together give me my group. So in that case, I have one group with 23 true, one group with 24 false, and one group with 24 true with these two records. So I have 3 groups in there. What's very, very important is I have my true grouping keys in there, and it should be automatic. Put them in here as well. Right. That's a very easy rule to respect. So the projection should include all grouping columns. If you try not to, you can, it will not complain about it. For example, you could group by century and captain, but only output the century. But put yourself in the shoes of the user looking at that, right? You see 23, 24, but you don't even know anymore why here you have twice 24 with 1 and 2, right? So this is why you shouldn't do that. It doesn't really make much sense, right? If you group by something, then you should also see in the output your grouping keys for it to make sense. Okay. Yes, go ahead, the microphone. Maybe. Yes, can you ask again, please, just so the people on Zoom?
So I understand it is not recommended to do that, but is it possible to do in SQL system?
I think it is possible.
Oh, okay.
This is exactly why I'm warning you about that, because it will not prevent you from doing it. It will actually do it. It could probably output something like that. But just because it lets you do it doesn't mean it's a good idea. So as a recommendation, try to get into the habit of automatically including your grouping keys in the outputs.
And one more question. So can you go to the next slide? So in this case, the century is 24.1. So 24.1 and 24.2 exist. And if there is 24.1 and 24.1, in this case, what happens?
That will work. You will get 24.1, 24.1. The reason is simply that PostgreSQL do bags semantics by default. So it will not mind if it repeats, right? It will not enforce set semantics. If you want set semantics, you need to add a distinct. You would need to say select distinct century count, and then it would eliminate the duplicates. But if you don't do that, then you can have duplicates. Right. Okay. This is actually one more reason why it would be confusing to people, right? Especially if then you have the same counts, then you don't know anymore what to do with that, right? Okay. We'll see actually, but this will be in a few weeks, that you might want to group by century and captain, but also to aggregate as subtotals per century. Right, you might be interested at the subtotals if you sum over the captains within a century. But this is something we'll see in a few weeks, because this has to do with data cubes and data warehousing, where you can actually do that. It's typically done with the top use case is sales data, when you want to record the sales, and when you want to group by quarter, by year, and so on, and you want the subtotals. But this is not something I'm doing today just yet. Right? Okay, but thank you for the question. It allowed me to clarify all these things for everybody. Okay, so group by was the new clause that we've just introduced. And here's another clause. That's the having clause. So you're going to tell me yet another clause. Yes, but it's kind of like the where clause. So this is the good news. Just think of it as a second kind of where clause. The difference with the where clause is that it's after the group by. So the where clause is before the group by. So the where clause is really a selection on the original table. The having is also a selection, but it's a selection after you have built the groups, right? So this is why in the having, for example, you can group on the centuries, and you can only keep the groups that have at least 3, right? Strictly more than 2. So you can then limit the output to the groups that are big enough. Who understands that this wouldn't work with the where clause? You cannot do that before grouping. Great, most of you. So in the where clause, you don't have the counts. You didn't do any grouping, right? In the where clause, you see record by record. You can say this record I want, this record I don't want. But in order to select the groups that have a specific count, you need to already have done the grouping. You can only do these counts after the grouping. So this is why you have to do it after the group by. And when you do it after the group by, it has to be called having and not where. I'm not exactly sure why they called it having rather than where. They could also call it where. Actually, in other query languages, in big data, they use where as well. I think it's probably not to confuse the users, and by giving them different names, then it clarifies that where is before you group and having is after you group. By the way, you see the design of the language, the choice of the name of the clauses, because it sounds like English. If you read that out loud, you select the centuries from the persons grouping by the centuries that have a count that is greater than 2, right? Having a count that is greater than 2. So the intent is that it's a natural sounding language in English. Who finds that intuitive? Right? It is intuitive, right? Okay. And what you get is 24. Why? Because 23 only has 1, right? There's only the first records right here for 23. So this is why it's excluded from this selection after the group by. And here we have 3 of them. So this stays. We don't need to include the, the counts in the output, because if all we're interested in, the question is, what are the centuries that appear more than twice? Then the answer is the 24th century. You don't care about the count. So this is why we didn't put it there. Okay. So now I showed you a bit of the query plans, which is just an abstract representation of what's going on inside the computer as the way to compute things. So if I have a query like that, what's going to happen is that it's going to take the table, it's going to use the where clause to filter out the records you don't want. Then it's going to group, then it's going to filter the groups, removing them, those that you don't want in the having clause. And finally, it's using the columns in the select clause in order to project to the columns that you want, potentially renaming some of them, right? Who sees that this is the abstraction of that, right? This chain of computations, right? So in other words, this is the what, this is the declarative language. You say what you want. This is the how. This is how it's done. And there can be many ways of doing that, not just this one. This is one way of doing it. This is the what, this is the how. And the really nice thing about SQL is that this is something the user doesn't need to see. This is something that the developers of PostgreSQL probably see because they implemented PostgreSQL in order to do it that way. But the user of PostgreSQL, you sitting in front of your Jupyter notebook, all you see is that. You don't even see that. Okay? So what's typically happening in a database engine, taking the time to, yes, we have a few more minutes before the break. What's actually happening in a querying engine is that when the user enters a query, the system, of course, look at the query, parses it, and so on. And then PostgreSQL will build the first guess of what the plan is going to be. So it's going to build something like that. And what's going to happen is that another piece of PostgreSQL, of the relational database software, it's called an optimizer. It's going to look at this graph. In general, it's a graph. It's going to look at this graph and it's going to find if there's anything inefficient in there. Maybe the way the query is written is a bit inefficient. And then the optimizer is going to rearrange this query plan, maybe removing some useless stuff. For example, imagine that you wrote where A is greater than 2 and A is greater than 1. So the A is greater than 1 is useless, right? Because you're also filtering by A greater than 2, right? So you don't need the A greater than 1. This is something that can be eliminated here. The optimizer is going to figure it out and it's going to drop the useless part of the query. This is the benefit of having a language like SQL. This is something that you don't necessarily get in Python or a different language. Python is just going to do whatever you want it to do, right? But in SQL, it's actually smart. It will figure out if there's anything in what you wrote that's inefficient, and it's going to take care of improving it for you. So the system is typically generating plenty of these query plans. Maybe there's like, it's like an internal competition within the computer that the engine is saying, okay, I'm going to try it in 5 or 10 different ways. Then it's estimating the performance that it's going to have, and then it's picking the query plan that it thinks is going to be the faster, and then it's using that query plan. And then you see the result on the screen. Okay. This is just the same thing. It's just that here it was more of a visual of the pipeline. Mathematicians or theoretical computer scientists, they like to represent it with the results on the top and the data flowing up, right? So at the bottom you have the table, then the data flows up. Right. In that case, it's just a single line because there are no joins or Cartesian products. That's the reason, right? It's just a pipeline from the bottom to the top. Okay. Okay, so this is just here repeating the best practices that I told you to be careful about. And again, these are recommendations because if you don't respect them, it might be you don't get any errors, but you might get surprising results. When you aggregate columns, have the habit of giving them new names. If you don't create names, the engine is going to create them for you, but sometimes either it's going to reuse the same name or it's going to give it the name of the aggregation. But then if you, let's say you use the same aggregation on several columns, like you sum over A and you sum over B, then you might get an output like sum 1 and sum 2, right? So that's not very clean. So in that case, you should really always give name. Whenever you aggregate a column, always add an as followed by the name you want to give it. Then you're in full control of your outputs. Second, I already told you, always put all your grouping keys, the one after group by, put them always in your select clause, all of them. Do not omit any of them. That's also a good habit. Then the next recommendation is to always include at least one aggregated column in the projected output. There can be exceptions in some cases, like the one I showed you with the having count, blah, blah, blah. But in general, if you don't add any aggregated column and you just want to look at the groups themselves, then you should use distinct. It's going to do the same thing, right? Because what does it mean to group over several columns without aggregating anything? It's the same thing as looking for the unique possible values of these grouping columns. Who sees that? Right. Okay, so you can think about it offline, but basically in a case where you have a group by with a few grouping keys and no having clause, and you're not aggregating anything, it is the same as just doing a select distinct with the columns you want. It's just easier. But don't worry, because as I said, the optimizer is anyway going to kick in. So the optimizer, even if you would do it with a group by, it would figure it out and automatically transform it to a distinct, but it's easier to read. Third, avoid aggregating grouping columns. You could, of course, try to count how many and so on, but it's kind of not the intent of the group by, right? So this is also where you're entering a territory where it's not easy to understand what that actually means. So typically you really aggregate the non-grouping columns, right? Not the grouping columns. So you aggregate within each group. And 5, do not use having alone. Having makes sense if you have a group by. If you don't have a group by, I'm not sure you will get an error, but you are entering fishy territory. It's exactly like the limit and the offset. If you use limit and offset without order by, I don't want to know what's going to happen. The same here for having without a group by. Okay. Okay. I think it's a good point to take a break, a well-deserved break, right? So we started with select from where order by limit offset. Now, who can tell me the total order of all the clauses we have so far? If not, I will do it, but do we have any volunteer? Yes, go ahead, the microphone. So try to give me all the clauses and guessing, because I think I didn't tell you the full order, but maybe you can try to guess.
From, where, order by, limit, offset, having.
Almost. So basically, the last part that I didn't tell you about yet is between group by and order by, which ones come first, right? So I didn't tell you yet if it's order by and group by. In fact, we group first and we order first, right? But this you couldn't have guessed because I didn't tell you. So you basically group and then you order. So it's select from, I might also make let me see if I get it right. Select from where, group by, having, order by, limit, offsets. I think I got them. That should be the order, right? Does it make sense? And also, so you know, it's very common that the keys that you sort by are also the same as the group by. So it's very common to do order group by AB and order by AB. All right? Does it make sense? Okay, awesome. Okay, so you deserve your break. So thank you very much. Also, thank you very much for your participation to the course. It's really great to have interaction. So see you in at 11:15 for the continuation.